is a privilege to address such a diverse and global audience today as a keynote speaker at the 6th International Conference on New Frontier in Engineering, Science, Law, Management, Humanities, and Social Science, INFES 6.0 2024. With participants joining us from 193 countries, this is truly is a global gathering of minds. I would like to express my deepest gratitude to the Chief Patron, Professor Dr. Rituraj Saikia sir, the Patron, Professor Dr. Caleb Mayo sir, the conveners, Dr. Dimitrios Karas and Dr. Rajesh Kannur sir, the organizing secretaries, Professor Dr. Annabella Monterio and Dr. Pratisha Kumari madam, and the coordinators, Dr. Sukhvinder Singh sir and Dr. Marichu madam, for their extraordinary efforts in bringing us together virtually. Today I will discuss transforming sand to silicon wafers, innovation in sustainable semiconductor production. These topics explore the critical role of innovation in semiconductor manufacturing and the sustainable practices that are becoming increasingly important in our industry. Thank you to everyone for being part of this significant conference. Let us dwell into the journey of sand to silicon wafers and the sustainable innovation driving the future of semiconductor production. So as you can see from the first slide, today we will see about how the silicon wafer can be produced from the sand. So as you know that sand is widely available onto the earth, and from that sand to the silicon wafer, how the semiconductor is being producing, that we will learn today in this particular presentation. So the first question in our mind that why we need to talk about the semiconductor wafer manufacturing, as we are very much witness in corona situation that the shortage of infotainment system in the four-wheeler as well as the electronics item, the key device in that particular vehicle or in electronics item is the semiconductor. So it is very much necessary for the current world, especially for the India, to move towards the semiconductor wafer manufacturing. And this is the first step, that from sand to the wafer and to the chip installation, and the whole combination of that will produce the semiconductor. So basically I have targeted 6 points that why we need to talk about the semiconductor. So first is the foundation of the modern electronics. As I already discussed, that it is the core component in most of the devices. Either it is a smartphone or it is the computer or in the electronics vehicle or in the four-wheeler. So the semiconductor is the must requirement to run or to generate the modern electronics. So this is the first foundation requirement for the semiconductor wafer manufacturing. Second, that is the complex and the critical process. So it is not that sand is directly converted into the wafer. There are so many processes in between that, and it is very critical and very we can say precise work we need to do to produce the wafer from the sand. So it is a complex and the critical process is the second point, which involves the sophisticated and the precise method. The third one is the economic significance. As you know that India is continuously growing, and if we need to reach to the highest level from developing to the developed country, it is very much necessary that we need to focus on majority of the part, and the semiconductor industry is the one of the part which can enhance the GDP of the India. So multi-billionaire dollar global industry and the driving economic growth along with the innovation is continuously required in the semiconductor wafers manufacturing. The fourth one is the technological innovation. Now it is not restricted to the earlier technology. As our current need is that earlier the phone size is very much big, but now the current generation needs small size phone. So we need not to restrict to the older technology. We continuously innovate the technology so that the chip size, the wafer size can be minimized, and more innovation can be integrated into for the semiconductors. The fourth is the key to develop small, faster, efficient devices in the semiconductor wafer manufacturing relevant to the various industries. Now, it is the fifth point is the supply chain reliability. The robust semiconductor supply chain, which can be percolated or can be available in various states of the country, and the relevant material required to manufacture is very much essential and with a faster rate. So it is the key point, that is the supply chain reliability is also necessary. The sixth one is the future industry growth. As we know that the semiconductor industries in which the Taiwan is pioneer, most of the semiconductor chips are being import from our country, from the Taiwan as well as another country. But if we need to grow fast, we need to cope up with that industry and can be situated in the country so that the future energy demand can be met or the future industry growth can be happen. So these are the 6 points that I highlighted, that why we need to uh, focus on this particular semiconductor wafer manufacturing. So this is the overall scenario, that how the wafer is being produced from the sand. So the chemical formula for the sand is the SiO2. So from sand, the next process is the metallurgical grade silicon, then electronic grade silicon, or we can say polycrystalline silicon, that is known as the CZ method or Chalsky method, and then single crystalline silicon, and then finally reach to the wafer. So there are series of process which involves into manufacturing of the wafer. So wafer is the in between point. If we need to produce the semiconductor, there are several process are available which can install the chip onto the wafer and produce the particular device which can be used in the electronics as well as into the vehicle. So today I'm only discuss about the sand to wafer, that is the intermediate part. If we really want to go for the semiconductor wafer manufacturing, there are several other processes. So in this particular slide, I have included sand to wafer. Now, as you know that sand is available onto the earth, which is also known as the silicon. Silicon or SiO2 is the chemical formula. So the first step in the semiconductor manufacturing is to obtain and purifying the silicon. So where we can find the silicon? So we can find the silicon from the sand. So it is the most abundant element in the earth crust, which is typically found in silicon dioxide. So the sand is also known as the silicon as well as the SiO2, which is available onto the earth. So this particular sand is not in a purified form. It is not in a pure form what we need. It is available maybe in a 98 or 90% purification of the silicon, but we need to convert 9N, that is the 99.79. Up to that much purity, we need to convert this sand which is available onto the earth and to the wafer. So you can visualize, or you can see that from 98 percentage to the 99.79, that is the 9N, that we need to conversion, or that we need to convert from sand to the silicon. Now this is the raw material, is the sand. Available is the starting material. The sand is available onto the earth. We need to transport ore by mining and reach to the industries. So this is the first step. Now the second step is from sand that is the raw material, convert into the metallurgical grade silicon. So this is the first stage, and the reaction is SiO2 plus C that gives SiO plus CO. We will discuss on to that particular reaction. So our first stage is the transform of sand or silicon available onto the earth converted into the metallurgical grade silicon. This is our first step. Now, how this metallurgical grade silicon can be produced? The first step to produce the metallurgical grade silicon is you require the electric arc furnace or electronic arc furnace. I will show the figure in the next slide. So in which you need to add sand, and with that we need to add some reducing agent. Reducing agent means either you can go with the carbon, either you can go with the coal or coke in which carbon is present. So the first stage is we have to use electronic arc furnace in which we need to add sand with the reducing agent, that is the coal. So combination of sand plus C will give the metallurgical silicon. So this particular mixture, when we are entering into the electronic arc furnace from 1600 to 1850 degrees centigrade to the 2000 degrees centigrade. So these are the various stages we need to give heat to this particular mixture. And because of that, the reduction process or reduction reaction can happen inside the furnace. So the high furnace temperature causes silicon dioxide, which react with the carbon, that is the reducing agent, will produce the silicon, and another produce, that is the byproduct, is the CO. So what we are getting in earlier, we have SiO2 along with the reduction agent, that is the carbon. With the high temperature, we can produce the silicon of the metallurgical grade silicon along with the byproduct, that is the CO. So environmental point of view, we can say that carbon monoxide is hazardous, but we need to establish some of the another industry to overcome this particular situation. So as the main agenda of this particular INFES 6.0 is the environmental science. So this relevant to that we need to focus on to. So this is the submerged arc furnace or the arc furnace in which the sand as well as the reducing agent is added. So first we need to give 1600 degrees centigrade temperature, so which can convert SiO2 plus carbon gives SiO, that is the silicon oxide plus carbon monoxide. Once again, it will react with the 2 carbon and will produce the SiC plus CO, and this SiC, that is the silicon carbide, along with the silicon dioxide will produce the individual silicon plus SiO plus CO. So our main focus is the Si. So from SiO2, first stage is to convert the metallurgical grade silicon, that is the Si. So from the bottom, liquid Si can be find out and can be converted into the metallurgical grade silicon. So this is our first stage, from the sand to the metallurgical grade silicon. Now our second stage, from sand to the metallurgical grade silicon to the electronic grade silicon. So in every step, we are trying to increase the efficiency or purity of the silicon. Earlier we have 98% silicon in the sand. Now we are going towards the 99.99. So the objective of this particular process is to convert the metallurgical grade silicon to the electronic grade silicon. So in electronic grade silicon, we are nominate this particular silicon is the trichlorosilane, right? So that is EGSI. EG means electronic grade silicon, Si to trichlorosilane, that is the electronic grade silicon. So this is our agenda to reach up to the 99.99. So in the trichlorosilane production, it reacts with the hydrochloride, that is, or you can say hydrochloric acid or hydrogen chloride gas. If we use hydrochloric acid, then we need to go with the liquid, but in this particular case, we are using gas. So we need to nominate is the hydrogen chloride. So the metallurgical grade silicon, that is the EGSI, will react with the HCl with the temperature of 300 degrees centigrade, will convert into the SiHCl, that is the trichlorosilane. So if you are not having the chemical background or chemistry background or environmental science background, you need not to worry. You only remember what are the basic steps, how the sand can be converted into the wafer. So this is the reaction in which Si plus HCl that gives the SiHCl3 plus hydrogen. So that is our trichlorosilane. Now the fourth process is the purification of trichlorosilane, that is with the help of fractional distillation. So maybe you are aware about the distillation process that is already covered in the high school as well as in the primary. So you might be aware about the distillation process. So in the combination of HCl with the metallurgical grade silicon in the fluidized bed reactor, that particular mixture will enter into the distillation for the purification. So this purification distillation column will separate trichlorosilane from the silicon chloride and impurities based on their boiling points. So the fundamental things of the distillation is to separate the various materials based on their boiling point. So this is the fundamental of distillation column. So we have metallurgical grade silicon converted into the trichlorosilane, enter into the distillation column. Now from that distillation column, we need to enter that particular mixture for the decomposition with the help of hydrogen at around 1100 degrees in the particular mixture. So that figure is available in the next slide, so you can easily understand the process. So the earlier process is the fluidized bed reactor, in which we need to produce 300 degrees centigrade. That particular mixture will add into the distillation column. The column purified the certain materials, and that certain materials will add into the Siemens type reactor. So this particular electronics grade silicon process is also known as the Siemens process. So the earlier is the EGSI and this one is the Siemens process. So in which we need to produce the 1150 degrees centigrade, and the SiCl3H and the hydrogen is added into the Siemens process will give the electronic grade silicon. So we have completed the two process. First is the sand, then metallurgical grade silicon, and then electronic grade silicon. Now our question arises that there are single crystalline, or you can say polycrystalline, or you can say monocrystalline. So we need to understand the difference. So the upper figure is the crystalline, that is the monocrystalline, or you can say single crystalline. So in which whatever the atoms which is available inside the crystalline is properly aligned. They are that the materials are not zigzag or not irregular, but if we can see the below figure, in which polycrystalline is the randomly situated materials. So this is the basic difference. So why we are studying this particular figure? Because our aim is to produce the single crystalline silicon or the monocrystalline silicon. We do not want polycrystalline. In this particular slide, you might not be understand why we are going with the single crystalline, but in the end of the presentation, you can easily understand that why we are going with the single crystalline material. So this is the basic difference. In single crystalline, the materials are properly aligned. In the polycrystalline, materials are not properly aligned; they are irregular. So this is the basic difference we need to know. Now, silicon is basically of two types, as I already told, polycrystalline, the single crystalline. The polycrystalline has the grain boundary or impurities. That is why they are irregular. In the contrast, the single crystalline having the no grain boundaries or regularly placed. So from EGS, we can produce ingot. So there are various new terminologies you can come across. First one is the metallurgical grade silicon, then the electronic grade silicon, which is process is also known as the Siemens process. Now we are going with the single crystalline silicon, or we can say that particular single crystalline silicon product is known as the ingot. Okay, so these are the basic steps. So from EGS is a pure silicon with some impurities in PBA, we need to move towards the high purity. Now we come across with the word ingot. So to produce that particular ingot, we need to go with the process that is known as the CZ-Chalsky process, or it is also known as the crystal growth, or it is also known as the single crystalline silicon. So whatever the silicon available in the electronic grade silicon will melt into the crucible which form the crystal. I will let you know in the next slide. And this particular seed crystal is slowly pulled up while being rotated, and you can form the ingot. So in this particular process we have to reach, or we have to produce the 1500 degrees centigrade. So from the figure you can be easily available or can be easily understood. So in upper part there is a name figure. So these are the crystal we have formed in the electronic grade silicon. Okay, so this particular electronic grade silicon crystal, when melted in the crucible, and from the figure C there is one rod is placed in that particular C area. So in earlier A figure we have various size of crystal. When we are melting up to 1500 degrees centigrade, it will form one layer of in a yellow color, and when we are adding the rod, and slowly that rod will absorb this particular material, and it will form one cylinder, conical cylinder, that is the last J diagram. So from A to the J you can see that we are producing the ingot. So from cutting different size of the crystal, we are moving towards the ingot. That is one form of crystal that is known as the ingot. So this particular process is known as the Chalsky process, or it is also known as the CZ process. So once again I am repeating, we have sand, then converted to the multi metallurgical grade filter, that is MGSI, converted into the electronic grade silicon, and into the ingot with the help of the Chalsky process. Now our focus is now from convert ingot to the wafer. So this is our agenda. So as you seen the earlier figure, in which we form one conical cylindrical, okay, that is ingot. So now this silicon ingot will cut off with the help of specific material. So we have ingot in a crystal form, but this particular silicon is a very hard and brittle, and because of that industrial grade or that brittle material, we can use diamond or industrial grade diamond to cut the silicon ingot. So our first step is to remove the end conical shape from the ingot. So this cannot be cut with the help of a simple material. For that you require the diamond grade material. So from both the side you are cutting down the uh, conical shape of the silicon ingot with the help of the industrial grade diamond. So this is how the first process of the ingot conversion. Now this silicon ingots into polysilicon requires some machine and chemical operation, that also we will see later on. And the trimming. So trimming means the first shaping operation is got ingot trimming, and this removes the seed and the tang ends from the ingot, and this is how the purification can be taking place. So in the first step, you need to do the grinding. So in goat, cutting down the end shapes which is available in the conical, then you need to do trimming so that the upper diameter part can be regularly precised size, and then still it is irregular. So to convert that irregularity diameter of ingot, we need to convert now into the surface grinding. So how the surface grinding is taking place, that is available in the figure. So whatever the cylinder form ingot is joint with the some support, and the upper part will remove the upper surface or the upper diameter, so that the same diameter from first end to the last end can be achieved. So this is our aim, to convert the irregularity diameter to the regular diameter. Okay, so this is the surface grinding. So this particular steps in which slightly oversized, because automatic diameter control in crystal growing cannot be maintained. In the CZ process, we are directly dipping this particular material and we are producing the ingot. So we have the irregular shape. Now we are converting into the regular shape and then converting into the specific diameter, that is known as the surface grinding. Now the next step of the surface ingot trimming that we have already seen. Now we have one cylinder with a specific diameter. Now we are moving slowly towards the chip manufacturing or wafer manufacturing. So the upper part is the ingot, is in the white color, and the below is the three cylinder which is circulated with the wire. So that is known as the diamond wire. So as we have already seen in the earlier slide, that this particular silicon ingot is a very brittle and hard material which cannot be directly cut with the simple material. So for that you require the diamond. So the wire which is circulated with the three brown color shape cylinder is continuously rotating, and ingot is pressed from the top to bottom, and that will convert the ingot into various different size of circular shape chip or wafer. So we are moving towards the wafer production. So this is known as the ingot slicing. Now, this is one particular diameter which produces or which can give the idea about the first steps to the last step. So in step one, we have ingot, then conical shape will cut down, then the proper diameter can be taking place, and this particular diameter is once again grinding, and then orientation can be taking place with the help of the diamond wire. So that is known as the ingot grinding and shaping. Now, from the shaping or to convert into the circular shape wafer, we need to convert this particular wafer into the wafer orientation. So in which we have total 6 number of figures. So based on the requirement of the manufacturing process, based on the chip you want to add onto the chip or onto the wafer, you need to cut down some of the area of that particular wafer. So if the first figure shows that the bottom part is cutting down, the second N type is having the another two type cutting down. So there are various orientation based on the manufacture and the application and the requirement of the customer. We need to fix the orientation of the silicon wafer. So we need to give the various names, that is the P type or N type, P type 111, P type 11100, like that one. Now, after fixing the orientation, we have to do the acid bath, that is known as the etching. Still, some of the shape at the time of orientation is not perfect, and the surface and edges is not properly maintained or can be damaged. So to properly making the surface smooth, we need to do acid bath, that is also known as the etching. So this can be done with the help of some chemical solution. So as you can see in the figure, the various slice of the wafer is placed in the chemical solution, and we need to um, remain steady for a few minutes, and then once again it can be converted. So after that acid bath, we need to do the wafer polishing. Okay, so in wafer polishing, as you can see from the figure, that the white color is the pad, and below white color there is a orange color, that is our wafer, and it is rotating in one direction. Similarly, there is another support of pad which is also rotating in another direction. So uh, the upper part and the lower part pad can be pressurized with each other, and also they are circulating in the same direction, and we are adding this slurry. So with the help of this particular mechanism, we are polishing the surface of the wafer which came from the acid bath. So that is the another process in which from acid bath the damaged surface can be smoothnized, and once again for the smooth polishing we are doing this particular process. So this is known as the wafer polishing. And finally, after wafer polishing, we need to do the wafer cleaning. So this wafer cleaning, from that you can see the solution is enter onto the surface of the wafer, and this particular chemical solution will remove the organic material. So still after polishing, after acid bath, there are organic material present onto the surface of the wafer, and to remove that organic matter, we need to add some material of mixture, that is ammonium hydroxide with the hydrogen peroxide, HCl H2O2 and H2SO4 H2O2. So with the help of this particular chemical solution, we can remove the organic impurities available onto the wafer. So this is the whole process from sand available onto the earth surface to the metallurgical grade silicon to the electronic grade silicon, then Chalsky process, then Siemens process, and converted into the ingot, then crystal growth, converted that ingot into the single crystalline silicon, and that single crystalline silicon can be transferred to the various process, and we are reached to the wafer, which is a purely polished and can be used to mount for the various device or chip which you can see on this particular slide. I hope you can have the better idea of the wafer manufacturing from the sand with this particular presentation. Thank you all the participants for listening my presentation. Thank you once again.